because we're not really introducing any new concepts in Chapter 18. We're just introducing the fact that there can be energy stored in a rolling mass. If you have a merry-go-round and it's spinning around, it's not translating. But does it have kinetic energy? Yes. So we have to account for that kinetic energy too. So rigid body work and energy, we're basically just saying the kinetic energy of a body that's undergoing general planar motion is not just the kinetic energy of its center of mass, which would be 1/2 mvg squared. That is translational. We have to add on to it 1/2. I bet you can guess this one if you don't already know it. What's the resistance to rotation? Moment of inertia. Very good. And then what is, instead of velocity, it would be? Omega. 1/2 ig omega squared. Look at that. You know this stuff so good you can come up with your own equations now. So we can have 1/2 mv squared is our translational kinetic energy, but we also have to add on to it our rotational kinetic energy. Okay, so for kinetic energy, we could have pure rotation or pure translation. This is just saying, it's kind of to zoom in on the specifics of general planar motion. If we just have translation, then the kinetic energy is just 1/2 mvg squared. If we added on the second half of that, omega 0. So of course that second half goes away if it's pure translation. If it's pure rotation, and we go about the center of mass, if the object were rotating about the center of mass, which it's not in this picture, right? If it were rotating about its center of mass, which is actually what happens if I throw something. My turn to throw something again. If I throw an object and I rotate it, in the air it's rotating about its center of mass. That's what it does naturally, because that's like the anchor point, right? That's where all of the mass averages out on both sides. So if it is rotating about its center of mass, then kinetic energy is just going to be 1/2 ig omega squared. And if we're in pure rotation, then Vg would be equal to 0. However, if the object is rotating about another point, a fixed axis that's not its center of mass, then we're going to have kinetic energy equals 1/2 I0 omega squared, where I0 is the moment of inertia about the axis it's rotating about. Okay? And we could add on to that plus 1/2 mvo squared, but we know that's 0 because O is not moving, right? How could I relate my I0 to my IG? Parallel axis theorem. We know that I0 is going to be equal to IG plus md squared. Just go ahead and plug that in. T would be equal to 1/2 times IG plus md squared omega squared. So T would be equal to 1/2 times IG omega squared plus 1/2 md squared omega squared. Okay, so that's kind of interesting. We have a d squared omega squared. In this case, the d would look like this. Is there any way to relate this distance to the angular rotation? That's acceleration. I think what you're thinking is just r omega. Right? We can say that the velocity of the center of mass is going to be equal to r omega, where r in this case is equal to d, because that's the distance between those two axes. So if I square this, Vg would be equal to, Vg squared is equal to d squared omega squared. So we're back to our original equation. So you can see that parallel axis theorem fits right into kinetic energy. It's amazing when math works. The other thing is work. We still have non-conservative work that can be done rotationally. You think of a moment, you think of your car, right? Your car is causing a moment to your tires, and that moment is causing the tires to spin. As the tires spin, your car is doing work. So the work of a force is still the integral of F dot dr. The work of a couple is spinning in the absence of force. Because if you remember a couple moment, we have two forces that are equal and opposite acting some distance apart. That's what a couple moment is. So if you do the sum of all the forces, it's 0. You do the sum of the moments, there's still a couple moment. That's very similar to your axle on your car spinning the tire. It's going to have a little force at the top and a little force at the bottom. Those two forces cancel, but the moment doesn't cancel. The moment's causing spin. So the work of a couple is just going to be the integral of m times d theta. Notice there's not a dot product there. Can anybody tell me why there's not a dot product there? Why isn't it m dot d theta? 2D, exactly right. This is only for 2D, there's no dot product. Because in 2D, all the m's are in the k direction. And all the thetas are about the k-axis. So the work of a couple is the integral of m d theta from theta 1 to theta 2. When the couple moment is constant, it's just going to be m times theta 1. Where did that go? It's just going to be m times theta 2 minus theta 1. So in other words, we have something that's causing a rotation. How far did we rotate? It's exactly the same thing as a force. We have something that's trying to push it. How far was it able to push it? F times distance, moment times theta. Okay, work of a weight and work of a spring. The only reason I even put this slide up here is because your textbook revisits it. And it almost looks like they're telling you something new. But they're not. It's exactly the same thing. There's nothing new from chapter 18 to chapter 14 on work of a weight or work of a spring force. It's exactly the same. 1/2 k s squared, 1/2 k delta s squared, and w delta y. No difference. We also make no difference whatsoever of these equations. Now, your book likes to separate out these two equations as if they're two different things. They even have different names in the book. Principle of work and energy and conservation of energy. It's the exact same equation. The only difference is the sum of the work from 1 to 2 in the top includes conservative and non-conservative. Down here, we've taken out the conservative work and turned it into potential energy. So the only thing that we've changed in chapter 18 from what we learned last week, your kinetic energy now includes translation and rotation. Also, non-conservative could be a rotating moment. Let's do a work and energy problem. I skipped the easy one so we could go right to a harder one. Basically, we have a very common object here, right? Springs and weights and all sorts of stuff. I don't know what it's doing, but we have to figure out how to use weight and energy to solve kinetics. So weight and energy and momentum are both just different forms of kinetics, right? We're solving for the forces that cause motion. Okay? So we have a 250-pound block is released from rest when the spring is unstretched. The drum has a weight of 50 pounds and a radius of gyration of 0.5 feet, about its center of mass. Find the velocity of the block after it descended 5 feet. I chose to set my datum at the block before it starts falling, which means my initial potential energy is 0 for the block, right? I also don't have anything moving at the beginning, so my initial kinetic energy is 0. My non-conservative work is also 0 because there's no moment being applied, there's nobody pulling on the string, there's no non-conservative work happening. So that means 0 is equal to kinetic plus potential, 2. So I got my equation right here, right? That's kinetic of the falling weight. That's kinetic of the spinning drum. That's potential of the weight after it fell 5 feet. And this is potential of the spring after it's been stretched. How many unknowns do I have? Got a whole bunch of them, right? I got a VB. I got omega. I've got a S. So how can I knock some of those out? VB equals omega R. Now this is where you have to set up your coordinate system just like we did before. I would set mine up this way, so I've got an X, I've got a Y, and my omega would go like this. If I have a positive omega, a positive Y direction, so it'd be VB equals omega R. There's no negative sign in that, right? Okay, good. Now how many unknowns do I have? 2. So what else can I do? Exactly. We do our old arc length trick, right? So as that string starts pulling down 5 feet, that is really just tracing the arc length of the drum. So how big of an arc length have we gone? Well, 5 feet. So we say arc length, S equals theta r. So we'll just say 5 feet equals theta times r1. So theta is going to be equal to 5 feet over r1, which is 0.75 feet. My units cancel, so what is my unit? Unitless, or what's the angle that's unitless? Radians, exactly. I just saw for how many radians I have spun. So my theta would be equal to 6.667 radians. So delta S is going to be that arc length, which is 0.375 radius feet times my 6.667 radians, which would be equal to 2.5 feet. Not too surprising it's half because it was half the radius. So I can plug that in and I get 0 equals 1/2 times the mass of the block, which would be 250 over 32.2 times V. What am I supposed to solve for? Velocity. VB squared plus 1/2. Now my IG is just that 0.5 m of the drum, which is 50 pounds. Okay, so that whole thing right there is just my I, my IG. And then I've got VB over R, which is my omega squared. And I'll have minus 250 pounds times 5 feet plus 1/2 times K, which is 75 pounds per foot times 2.5 squared. So we have an equation. We got one unknown. We can solve it. And VB is equal to 15.5 feet per second. It's going downwards.